A clock on a fast plane ticks a tiny bit slower than one on the ground. A GPS satellite must correct its own time every day to stay honest. Stand still long enough, and the universe itself keeps a slightly different beat around you. If time can change its speed, is it really a single universal river, or is it a fabric that bends with motion and gravity, only pretending to flow? We are about to ask what slowing time actually means in daily life. We will test the idea with simple tools, careful logic, and modest claims. The excitement is real, but we move with patience and clear eyes. The story continues in the next part. In 1905, a young patent clerk named Albert Einstein was studying how light behaves when you move through it. He was not working in a lab or surrounded by equipment, only with pen and paper, yet his thoughts changed how we understand time itself. Before Einstein, time was treated like an invisible stage on which the universe performed its play. Every clock was assumed to tick together everywhere, always. Newton called it absolute time, constant, independent, and perfect. But the late 19th century was a time of confusion in physics. Experiments with light were failing to prove the existence of the ether, a supposed invisible medium that carried light waves. Instead, they hinted that light had a fixed speed no matter how fast you moved toward or away from it. This was not just a small detail. If light's speed never changes, something else must. And that something was time itself. Einstein realized that clocks in motion must slow down to preserve this universal constant. It was a radical trade. The speed of light stays fixed, so time becomes flexible. The world learned of this through his theory of special relativity. It wasn't about complex equations or abstract symbols at first. It was about everyday comparisons. A traveler moving fast through space would simply tour the experience less time than someone at rest. Why does this matter today? Because every satellite orbiting above you lives this truth. Without accounting for relativity, your phone's GPS would drift by kilometers each day. Timekeeping, once a simple matter of ticking gears, is now a dance choreographed by physics itself. How far can this flexibility go? Can time stop completely or reverse its direction? So far, every experiment says no. But even our best instruments can only measure so much, and every new test seems to push the question a little deeper. Imagine two friends comparing their watches, one standing on Earth, the other flying in a high-speed jet. When they meet again, the traveler's watch shows slightly less time passed. It's not a malfunction. It's the universe revealing that motion and time are connected. To picture this, think of time as a stretchy fabric, not a rigid ruler. When you move faster, that fabric stretches around you. Your clock, heartbeat, and every atom inside you slow their rhythm compared to someone at rest. This effect is called finite time dilation, though Einstein preferred to describe it as the natural geometry of space-time. In simple terms, time dilation means that moving objects experience less time between events. Technically, it arises because the speed of light, about 300,000 kilometers per second, remains constant for everyone. If you approach that speed, the equations of relativity demand that time must adjust to keep light's speed unchanged. Gravity plays a similar trick. Picture a ball rolling down a curved surface. The steeper the curve, the slower it moves forward. Massive objects like Earth or the Sun bend space-time, creating slopes in this invisible fabric. Clocks closer to the mass tick slower, while those farther away run faster. Einstein's later work, general relativity, unified motion and gravity into one principle. It showed that both movement and mass reshape time itself. Not symbolically, but physically, an effect that can be measured with precise atomic clocks. How do we know this isn't just theory? Because we've tested it. Jet planes, satellites, and even clocks placed at the tops of buildings all confirm the same pattern. Time is not absolute. It's elastic, tuned to the rhythm of motion and gravity. But what exactly keeps this fabric stable? And could it ever tear or fold in ways we cannot yet imagine? The deeper we look, the more time behaves like a living structure, not a passive background. In 1971, two physicists, Joseph Haefel and Richard Keating, carried 4 atomic clocks on commercial flights around the world. When the planes landed, the clocks disagreed with identical ones that had stayed on the ground. The difference was tiny, a few billionths of a second, yet exactly what Einstein's equations predicted. Time had moved more slowly for the clocks in motion. A few decades later, scientists placed 2 synchronized atomic clocks at different heights. The one just 33 centimeters higher ticked slightly faster because gravity's pull was weaker there. Even this small vertical shift was enough to bend time's rhythm. These are not isolated curiosities. They form the foundation of modern navigation. Each GPS satellite carries a highly accurate atomic clock. Because they orbit farther from Earth's gravity and move quickly, their time would drift if not corrected daily. Without that adjustment, your phone's location could be off by several kilometers within hours. Another example comes from particle physics. Muons, unstable particles created by cosmic rays, live longer when moving near the speed of light. On Earth, they should vanish almost instantly. But because of time dilation, they survive long enough to be detected at sea level. Their very existence on the ground is proof that time slows for fast travelers. Each of these experiments turns a philosophical idea into measurable evidence. Time is not a single universal beat, but a pattern that changes with speed and gravity. And though these differences are small, they compound over distance, creating a delicate architecture that our entire technological world depends on. What does this tell us about the nature of reality? It suggests that time is not something we observe. It is part of the machinery that shapes observation itself. If time slows for motion and gravity, does that mean it is a physical thing that can stretch and bend? Or could there be another explanation, one that makes time appear flexible without it truly changing? The null hypothesis begins with simplicity. Maybe our clocks, instruments, or reference frames are imperfect. Perhaps what we call time dilation is an illusion caused by measurement limits, synchronization errors, or the way motion distorts perception. Early skeptics of relativity ask these same questions, and for good reason. Extraordinary claims demand extraordinary proof. Let's start with the idea that the clocks themselves might be faulty. Atomic clocks are built to count the vibrations of atoms, the most stable oscillators we know. If movement or gravity changes those vibrations, that is not a mechanical flaw, but a shift in the behavior of matter itself. And this is exactly what experiments reveal. Every kind of clock, mechanical, atomic, biological, slows down equally when exposed to the same conditions. That makes human error an unlikely culprit. Another alternative is that space itself could change while time remains constant. If motion compressed physical distances instead of stretching time, we might see similar effects. Einstein's equations, however, show that both length and time change together, locked in a single space-time relationship. You cannot alter one without touching the other. Some physicists have also explored whether time might emerge from deeper statistical rules, not as a dimension but as an effect of entropy, the tendency of systems to move from order to disorder. If that were true, slowing time could simply mean a slower unfolding of change. This idea remains open, fascinating, and unproven. So which explanation fits the evidence best? All precise tests, from satellites to subatomic particles, match relativity's predictions to an astonishing degree. No competing model yet reproduces those results as consistently. It appears, at least for now, that time truly bends with motion and gravity. But the search for alternatives continues, because in science, even the most elegant theories remain hypotheses awaiting their next challenge. Even with precise clocks and powerful equations, our picture of time remains incomplete. We can measure its slowing and stretching, but we still do not fully understand what it is. Our instruments can only sample narrow slices of the universe, leaving vast areas beyond reach. One limitation lies in scale. Relativity describes large systems, planets, stars, galaxies, while quantum mechanics governs the tiny world of particles. At the smallest scales, time seems to lose its continuous flow, behaving more like discrete pulses than a smooth stream. No current experiment can bridge this gap cleanly. Measurement also has its limits. Atomic clocks can detect changes as small as 1 part in 10 quadrillion, yet they still rely on vibrations of matter bound by energy and temperature. At cosmic scales, our telescopes read the past through stretched light from distant galaxies. But those signals have already aged billions of years before reaching us. Between these two extremes lies a silent zone where no device can yet observe how time truly behaves. Even definitions create problems. Is time something that flows, or is it simply what separates one event from another? If the universe were frozen, with nothing moving or changing, would time still exist? These questions lie at the intersection of physics and philosophy and remain subjects of ongoing analysis. To reduce uncertainty, researchers plan and evaluate new experimental methods. Quantum clocks using entangled atoms may allow measurement of time at scales where gravitational and quantum effects overlap. Space missions could carry synchronized instruments to test relativity in regions with minimal influence from Earth. Each attempt is a step toward determining whether time is fundamental or emergent, shaped by deeper physical laws that are not yet identified. If the slowing of time is real, its effects extend beyond physics. In technology, it maintains the function of global systems. GPS navigation, satellite communication, and internet time coordination rely on continuous relativistic adjustments. A single uncorrected microsecond can alter an aircraft's trajectory or disrupt financial processes. In science, it affects how the universe is interpreted. Time dilation is used to explain the arrival of certain cosmic rays, the behavior of black holes, and the presence of the cosmic microwave background. It also influences how astronauts age during high-speed travel, producing a small but measurable difference compared to people on Earth. The scale is minor, but the principle shows that motion changes the rate of experienced time. At a human level, the idea that time is not absolute influences how events are viewed. Moments can be understood as intervals shaped by context rather than fixed points. A quiet morning sense of passing time is as valid and as relative as the reading of a distant clock. There are also risks of misinterpretation. Popular culture sometimes represents relativity as a way to reverse aging or move through time. In practice, the measurable effects are small in ordinary conditions. Confusing figurative descriptions with scientific mechanisms can result in inaccurate conclusions. Understanding the variability of time encourages a more careful perspective. It indicates that human intuition does not always align with how the universe functions. Every measured second is influenced by the structure of space and gravity. If this balance changed even slightly, systems, perception, and definitions of experience would require adjustment. The more time is studied, the more complex it becomes to define. It is influenced by gravity and motion and affects the behavior of physical systems. It cannot be observed directly, only through its effects on clocks, particles, and memory. Time may function less like a flow and more like a set of relationships shaped by position and movement. Each second is part of a larger structure connecting matter, energy, and conscious experience. Relativity does not reduce complexity. It clarifies how these relationships operate. Observing simple events, such as a sunset, involves interactions between speed, distance, and gravity. Identifying time as flexible is informative. A more significant point is the ability to detect and measure this flexibility. Every finding about time is produced by observers who are themselves subject to it. Scientific study continues, despite this limitation, and still reveals the structure of the system. Interest in the subject is reasonable, but so is the need for careful interpretation. Time remains both a condition and an unresolved concept. This makes each moment suitable for examination. If you found this topic interesting, consider subscribing and sharing your thoughts in the comments.